are officially going now.
Are you recording?
I am recording. Now, let's review one of the best days of your college career last time we met, where we used this applied math to actually make this refrigerator art. Then I said, I wonder if there's a better way to do all this. And we could have left all of these variables in here and come down and solved it. So pull out your formula sheet. Pull out this formula sheet. So on this formula sheet, we'll go down here. Where's WNC? On the next page? I don't know. Okay. So, here's our chapter 7 work. Force times distance, cosine theta. Here's our kinetic energy. Here's our net work. And we can add to this, which is equal to the change in kinetic energy. Right? Our net work is equal to change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. Here's our potential energy, mgh. They have potential energy due to gravity. Then this is potential energy of a spring, and we actually pretty much did that, but that's for a spring. This is how much the spring, distance the spring is compressed. And I think we didn't do that, but I'll just clarify. X is distance here. K is a spring constant. So this is the, X is the distance the spring is compressed, and this K would be a spring constant of Newton per meter. No, this is a spring constant, Bob. You just got to get over it and move on with your life, Bob.
I will in about 4 weeks.
4 weeks, huh? Spring constant. Now, this right here is just change in kinetic, or this is total energy. This is kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final, right? That's just conservation of energy. And then they put some work in there and stuff like that. WNC is work from a non-conservative force. Work done again. And we didn't do really any efficiency, work out, energy in, but we did power down here, right? I don't know if we calculated that number in the last lab like I thought we were going to. Okay, so that's what we did for chapter 7. For chapter 8, it adds momentum, which is just mass times velocity, right? P is momentum. Power. Capital P is power. Big W is work. Waste. Anyway, now let's add to the bottom of this. Now this is impulse right here, right? Change in momentum is equal to the force times time. That's our impulse. No, change in P or change in momentum is impulse. That's kind of where we started this chapter right away. We did this impulse momentum theorem. If momentum is conserved, the initial momentum equals the final momentum, or you'll see a prime on this. This little prime means final. Or P in, yes. This is the same, what I'm just saying is this is the same thing. I'm just saying that's the same thing. Maybe I shouldn't have put that down. I'm just saying P final is the same as P prime. Now, let's take our example we did last time, and here is a standard equation we can do. M1 is going to move that way with V initial 1. Yet if it hits M2, we can add this right here. If it hits M2, when V2 initial equals 0. That is not very clear. There we go. Now, we did this problem where this was 0.5, this was 4, this initial velocity was 0, this was 3.5 kilograms, right? That's the problem we just did. And everybody loved it. It's a good problem to do, good applied math to make refrigerator art, but now we can cheat. Here's what the results are. This is an elastic collision . And we have to say that this one is at rest. In the beginning. This is what you're going to get. And we could put these in parentheses. That's going to be our final velocities, right? After collision. We'll put it like that. How's that? Those will give us our final velocities, all dependent upon what V1 initial is, correct? And a ratio of the masses. So we should be able to get, let's see, V1 prime was -3, correct? Yeah, from last time. So I think we could do it in our head. Yes, we can. This was 0.5. This was 3.5, right? So that's -3 for that one. That's -3. And this right here would be 4, right? M1 plus M2, 0.5 plus 3.5 is 4. We have -3 over 4, right? Then wasn't V1 initial 4? No, this came in at 4, though. This was the initial velocity of 1 came in at 4, right? So 4 here times the 4 down below would cancel out. Wasn't my numerator -3 here? So it works. This is from the problem we did, right? We ended up with V1 prime -3 and V2 prime was 1. So if V2 prime was 1, 2 times M1, M1 was 0.5, 2 times 0.5 is 1. This is 4. This is 4. The 4's cancel out. Again, V2 prime is 1. It works. Not as much fun to just plug this in and not know what's going on. When we come up with these results, we're really using 2 equations, 2 unknowns, and we're using all of this with conservation of momentum and conservation of kinetic energy. Oh, it's just beautiful. It's just beautiful. It hurts. Conservation of momentum does work for inelastic collisions. Kinetic energy does not. So when you did lab, that last question, how much was lost, it was quite a bit, I think. Now, do you have the labs submitted? If not, get those done like by tonight, because anybody that doesn't have a lab submitted, because we have lab today for the other class, for the noon class, and then we'll get everything submitted. If you haven't submitted, I'm going to throw a 0 in there, and there's no going back. Then I'll email you the spreadsheet that has all the data in it, or has all the stuff in it. All right? Then I can grade it. Hopefully on 2 screens so I don't have to print them, but we'll see. Okay. Oh, man. Conservation of momentum and kinetic energy. Okay. Let's look at this problem from the book. At first, I don't know if I cared for this problem, but I guess it's fine. We got more hockey people around this area, huh? And this kind of makes sense. Okay. So here's what we have. First of all, if this hockey puck's coming in and it's going to be caught, this is inelastic collision, correct? If it is inelastic, what is conserved? Momentum is always conserved. Kinetic energy, not. Right? Right? Momentum's always conserved. Kinetic energy, not. This is going to create heat. So we're on, this is example 8.5, so I'm going to move up here. We're going 8.5. Calculating velocity and change in kinetic energy. Inelastic collision of a puck and a goalie. Find the recoil velocity of a 70 kilogram ice hockey goalie originally at rest who catches a .15 hockey puck slapped him at 35 meters per second. So let's do that. Let's go up and start this. We'll start it on this line right there. All right. Right away, I would try conservation of momentum no matter what. And we're going to say the original momentum is equal to momentum prime. That's small p, Bob. Small b, Bob. Small. They're both small for momentum. Both small for momentum.
Well, they might be bigger than the L.
You're right. I might have messed up. All right, so let's see what we got here. This would be the mass of the puck, velocity of the puck, plus the mass of the goalie, velocity of the goalie, would equal to velocity of the puck prime, plus mass of the goalie, velocity of the goalie prime, right? That's all just conservation momentum. Now, this is going to shake out nicely. Well, the goalie's at rest. So we're going to put a 0 here, correct? But here's what we know. These V primes are going to be the same. Just like when you shot the ball into the catcher, the ball and the catcher are going the same velocity up. So we know that V prime of the puck equals V prime of the goalie. It's the same. Let's just use V prime then. Right? We're just going to use V prime. And we're going to factor it out. So we factor this out. We're going to have V prime is equal to mass of the puck plus mass of the goalie, right? It's the same velocity. So mass of the puck plus mass of the goalie. So we have mass of the puck, velocity of the puck equals we want this velocity. What? Because this is an inelastic collision, and last time we did elastic. But this is just like our example we did where this was the mass of the ball plus the mass of the catcher when you use conservation of momentum. This right here was the ball coming in, right? This was the ball coming in, then it was going to have a velocity after the catcher and the ball head up with the velocity. So we're looking for this, so we're simply going to have the mass of the puck, velocity of the puck, divided by mass of the puck plus mass of the goalie equals V prime, right? And if we plug this in, we're going to have mass of the puck 0.15 kilograms. Velocity of the puck 35 meters per second. Divided by mass of the puck plus mass of the goalie and it's not going to be very much. I mean, that puck doesn't have very much mass. So this is not going to be very much at all, but it'll be a little bit here, and we get what? So we get what? Yeah, 0.075. 0.075 meters per second, huh? Okay, so that's, this is very, very, very typical for an inelastic collision. What is the velocity after collision? Realize if they're entangled together, then the velocity is the same. This part right here. Okay. Oh, okay. Yeah, that'll make it different. This is a plus sign down here? Okay, let's do part B. So this was A. Let's label this A. There's a part B. Momentum is conserved, kinetic energy is not. So for part B, it wants to know how much kinetic energy is lost during the collision. Assume friction between the ice and the puck goalies is negligible. We're really talking about the friction, the heat generated when the puck hits the glove. We're talking about when the puck hits the glove, we lose energy here. So, what is kinetic energy initial? The kinetic energy initial is just 1/2 mass of the puck, velocity of the puck squared, right? The goalie's not moving, right? Kinetic energy of the goalie is 0. I'll put a G here. Stop, K-E-O-P. Kinetic energy initial puck would be this. Kinetic energy initial goalie would be 0. It's not moving. So we're going to have 0.5. That puck is 0.15 kilograms. And that thing is coming in at 35.0 meters per second squared. Now we get what? How about 91.9? Okay. I think we get 91.9 joules, don't we? Yeah, make sure that's squared right there. So this is, that's the kinetic energy initial, correct? Now, the kinetic energy final is going to be 1/2 times, I'm going to write it in first, mass of the puck plus mass of the goalie, V prime squared.
I cuss so much in this class. It's not even-
You try to change your ways, Bob.
I'm trying, dude, but you're not helping.
Let's plug this in. This is my V prime that I just figured out, right?
That thing on the line is the G, correct? Mass of the goalie?
Yeah, mass of the goalie. All right, so now this right here is 0.15 kilograms and 70 kilograms. Now, what's those calculators give you? .197 joules. That's what you got. 0.197. I just put my arrow there.
Well, I got too many calculations now. So I put the 35 back.
We can put some kind of Bluetooth thing where he has to put one of his gauges to square it right there every time in his ear. 0.197, right? Now, what percent, let's do this. What percent is lost? If we did percent lost, we would do the part lost. Percent is part over the whole, right? Well, what do we have left? We started with 91.9 minus 0.197 over 91.9, right? This is what we started with. This is what we have left. So this is how much lost, the joules lost in the numerator. So the part over the whole is the part lost, right? If we multiply this by 100, we lose a lot. And it is 90, what percent? 99.7%. Okay. Let's figure out this next one. I think this is the problem here. So we are doing an inelastic collision again. This system here, let me rewrite it on the top over here. Expert drawing up here first.
Sure would be nice to see it.
Oh, sorry. Cart 1, M1, carries a spring with initially compressed during the collision. The spring releases potential energy and converts it to internal kinetic energy. Okay, let's see what we've got here. I'm going to draw this out. This is M1. Got some kind of spring on this. This V1 initial is 2 meters per second going to the right. Well, I think the spring is going to hit the other one yet. I'm not sure. The mass of the spring in the cart is 0.5. Let me see how this... So this is 0.350 kilograms. Figure 8.13. Let me go... Yeah, it's just saying that they're going to collide and bounce off. Just like I had it on the air track, I used a rubber band in there. So it's just saying they're going to bounce off. Okay. So here's what we've got. We've got another mass over here. And this is just like an air track example. This is mass 2. This mass is 0.5 kilograms. This is going this direction at V2 initial is minus 0.5. So this, again, this spring is just going to spring back. Then, let's see what we've got. So, So this is 2. Cart 2 is M2, has a mass of 0.5, its initial velocity is negative 0.5. After the collision, do we have this drawing? We're good so far? Yeah. After the collision, cart 1 is observed to recoil with a velocity of negative 4. What is this number? What signage do I use for this after the collision? This is V1 prime, right? We know that V1 prime after the collision is negative 4. It says, what is the velocity of cart 2? So we need to find V2 prime. Okay, what type of collision do we have? Elastic. Can we use the cheater equation I gave you? No. Why not? Because this one's already moving, right? That cheater equation I gave you is only for one of those, for this is at rest. Nah, but this is going to fall right out. This is going to fall right out. This is going to fall right out. We're going to use conservation momentum. Right? So momentum 1 plus momentum 2 equals momentum of 1 prime plus momentum 2 prime, correct? Now we're going to need, so momentum 1, mass 1, V1 initial, right? So you're going to have M1 V1 initial plus M2 V2 initial. Why am I putting them up there? They go down there. Equals M1 V1 prime plus M2 V2 prime. This is going to fall right out. Right? Nothing new there? What are we looking for? We're looking for V2 prime. I know everything, don't I? I know V1 prime after the collision is negative 4. We just got to make sure we keep track of all of our signs. Take over to the other side. Instead of plus right here, it's going to be minus on the other side, right? Oh, I'm not going to put the numbers in first. Oh, I can't do it. I can't do it. Not when I can factor things out. It's going to be all of this, because I could factor an M1 out. Well, you could, but you don't want to put numbers in first because you want to realize that maybe one of these variables cancels out. We're going to divide all of that by M2, correct? And that should give us V2 prime. Now, we just got to make sure we keep track of our signs in this pig. So I'm actually going to we could factor out, we could put our M1s together and factor it out, but no, just be M1s we'd factor it. But let's just leave it the way it is. Let's just leave it the way it is. So mass 1 is 0.35 kilograms. Oops, and why'd I write 0.5? V1 prime is 2. Mass 2 is 0.5 kilograms. I'm going to get rid of my units. I know I've got kilograms and meters per second. V2 initial is negative 0.5. V1 prime negative 4. I don't know. It looks like it's supposed to be 0.35. This is 0.35, not 3.5.
Sorry for the people writing it in.
Okay, how's that look? What do we get? Momentum is conserved. This is elastic. They are bouncing off. Yeah, that's wrong. Because they're not stuck together. So that is a typo. Okay, conservation of momentum. Doesn't say they're stuck together. Impulse is your force times the contact time equals your change in momentum. So impulse is force times contact time, or it's change in momentum. It's the same thing. So you can do it with either way. So I say, what's the impulse of this? Use force times change in time on one side, or change in momentum on the other side. Should be equal. No, because, yeah, this one has to be at rest. Right. Okay, now, how much energy was released by the spring, assuming all of it was converted into internal kinetic energy? So, oh, the spring was compressed when they hit. We'll just skip that. Oh, we can figure it out. We'll figure it out quick. B, how much kinetic energy initial do we have? Kinetic energy initial is going to be 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. That's kinetic energy initial, right? Two is the initial velocity. Isn't that? .35 is M1, V1 initials 2. M2 is 0.5, V2 initials negative 0.5. Right? So our initial kinetic energy is .763. Now, any extra has to come from the spring, so let's do kinetic energy final. So if we plug this in, V1 prime was -4. And we calculated V2 prime to be 3.7. We get a kinetic energy final equal to 6.22. You should get 6.22 joules. So the spring gain of 5.46 joules. Yeah, 5.46. All right. What is this?
Is that 3.7 supposed to be 3.7 or 0.37? Right above.
No, it's 3.7.
Okay.
We're not getting 6.22? And the mass is 0.5. That's 0.35, yeah. I've got it. Yep. 0.5 times 0.35 times 16 plus 0.5 times 0.5 times 3.7 squared equals 6.22. Yeah, we should get 6.22.
So oh, dude, I'm not even close to any of those numbers. I don't know what I'm doing, how much it is. Oh,
Okay.
I don't know if you have time. Yes, I was getting
It's not gonna be. It's gonna stay above 34 tonight. It's just gonna be slushy. You'll be all right tomorrow morning yet. You should be, because it's only get down to 34. Okay, let's look at this. Now, you can if you got it done. Okay, we have done this. What's this? Elasticity and restitution already. I needed a filler lab one day. We calculated G with this. Remember, we did the timing of the bounces, basically? We did something that looked like, this. And I was mad because whatever balls we had, then I turned around and ordered these golf balls on Amazon. And this is all, golf balls seem to be like fishing lures. You only got to catch a fisherman, you don't have to catch a fish. Every golfer thinks if they get new balls or new clubs that they're going to be a better golfer. And then they've got this type of thing where, we can get the green version of these golf balls. I guess I've got this orange version because it's orange. So what did I buy? I bought, I don't know, Tour Velocity, I guess. I need to go on tour. So now I need to tell somebody I need to go on tour to wherever, maybe Florida golf course, to do this because I have tour balls. I don't know, but enhanced feel around the green. I guess a golf ball has feelings or grippers or something. This is just whatever. Marketing, huh? Somebody had to, you got to reinvent something about a golf ball or a club, right? You're going to make it out of titanium, alloy, bismuth, something, so you can sell more golf clubs. But anyway, we have this concept called elasticity. And basically, it is a ratio. I'm going to just, for simplicity, because I could go on how we get to this, using conservation of energy, what velocity does it have when it hits the floor, what velocity does it have when it goes back up, we can get the coefficient of restitution this way. So this is our coefficient of restitution. Now, let me show you when I've worked this out, because I think you're going to be underappreciative of all this, so I'm going to just show you. No. This is how this starts out. We have to take kinetic energy and momentum. We rearrange this, cross out the halves in the kinetic energy. We rearrange it, cross out the halves, factor out an M1, because there's an M1 here and there's an M1 here. So then you'd end up with V initial squared minus V1 final squared. Right, you got to throw it over the other side and subtract it. You could also do the same thing with the finals, or with the twos. And then from momentum, we would have this. But if we divide them out and put a line over top of these, now I have kinetic energy over momentum. And I start trying to reduce this and factor things out. But look at FOIL. This V1 initial squared minus V1 final is the same as this down here, V1 initial minus V1 final times V1 initial minus V1 final, V1 final, right? So I'm deriving this and eliminating things. So I'm taking a ratio of the kinetic energy and the momentum, and I can come up with my coefficient of restitution for elastic collisions of being this ratio. V2 final minus V1 final and all that. Velocity. When this hits, what's that? E is elasticity, or our coefficient of restitution, elasticity. What's that? Because we can use E for this. But now, if you go back and expand this, here's our height 1 potential energy, kinetic energy, and blah, 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 blah. If you calculate this all out, we get this ratio, and it comes down to the square root of H2 over H1. So, for our coefficient, they'll call this the coefficient of restitution, or elasticity. square root of h2 over h1. And there might be one question on that, and that's it. But so I didn't want to go through all of that derivation. It's a sweet derivation, Bob. I will stay after class to go through that whole derivation with you.
Before I put my answer there.
So, at this point, we are done. Yeah, we can put that on there. I don't think it's on there, is it? Let's put it right up here. This really, because this up here is just, we don't need this. We're not doing collisions in 2 dimensions, so we're not going to be using this stuff down here where it's got cosine theta 1. Well, Bob, I know you want to do theta 1 collisions and theta 2 collisions, but we'll have to hold on. So E is the square root of height 2 over height 1. Now,
All that other stuff first.
let's draw this out. So if this bounces up, and obviously this should be height 1 and height 2. Huh? Would look something like that. All right, so our goal then is to bubble that quiz before the end. We could have some questions in the beginning, right? So try all the quiz questions, all the homework questions, and tomorrow we'll figure that out. All right? So I'm not going to hand you the bubble sheet the first minute you walk in the door. We'll have a few questions to work on, okay? Fair enough?